got good terrain now. You back here? Yeah, we're safe now, except for the mirror.
In August 1949, there have been 4,600 air crewmen who have punched out. Of these, if we concentrate on the ejection survival rate for the last 5 years, we see a less optimistic picture. Here, the survival rate average drops to 75%. Accident analysis reveals that the majority of these fatalities were not due to mechanical problems, failure of the egress system, or improper parachute landing technique. Rather, they were the direct result of delayed ejection. The Air Force Inspection and Safety Center is well aware of this problem.
Single motion initiation, rocket catapults, automatic opening lap belts, ballistic powered inertia reels, seat man separators, seat stabilization devices, force deployed parachutes, and automatically deployed survival kits are just some of the improvements which were designed to facilitate crew members' escape. Some of our newer aircraft, such as the A-10, the F-15, and the F-16, are equipped with the new ACES II ejection seats that even surpass our other highly refined escape systems.
Yet, in spite of the many safety improvements, escape technology is still having a hard time keeping pace with demands placed upon it by improved aircraft performance, more complex missions, and more low-level flying now required in the current training environment. There must be time for the ejection sequence to fully operate prior to ground impact. This is borne out by the high fatality rate in escape attempts outside the performance envelope of the system, at low altitudes, particularly below 500 feet.
No matter how good the escape system, you've got to give it time to work. As flight surgeon at the Safety Center, I reviewed many accident reports involving the delayed ejection, and they always illustrate at least 2 points. One, these seats require a finite amount of time to work. For example, depending upon the airspeed, the rear seat out of the F-4 requires 4 or 5 seconds from initiation to full parachute, and the front seat takes a second longer. And second, these systems were not designed to overcome the horrendous sink rates generated by aircraft out of control, which may exceed 600 feet per second. There's a good reason for those mandatory bailout altitudes. You just don't have much time. Not long ago, an F-4 crew was defending during a similar air combat tactics engagement, and while pressing to defeat his attacker, the young pilot departed his aircraft at roughly 8,000 to 9,000 feet AGL above an overcast. Now, he had a reputation as being an aggressive, up-and-coming good stick, and he tried hard to salvage his mistake. But apparently, he got a secondary stall to avoid going in the overcast, and in they went. While passing through the overcast, perhaps they became disoriented. We'll never know for sure. But one thing for certain is that both he and his Wizzo lost awareness for how fast that aircraft was really coming down. We have indications that that aircraft dropped the 8,000 or 9,000 feet in less than 16 seconds and possibly as little as 11 seconds for an average sink rate of between 500 and 700 feet per second. When it passed through 4,000 feet AGL, still unrecovered, it was going to crash and was fuel to stay with it. But when the aircraft broke to the bottom of that 1,500-foot overcast, with them still aboard, they were both dead men. The Wizzo did initiate a dual-sequenced ejection at something around 1,000 AGL, but barely achieved man-seat separation when he hit the ground. Amazingly, though the impact broke his thigh, that's not what killed him. He burned to death in a fireball.
Making the ejection decision in a wartime environment does not seem to be a problem. We know from our experience in Southeast Asia that there was little reluctance for crew members to go out of a battle-damaged aircraft. Their decisions were made quickly, almost automatically, without hesitation. As a result, there was a 95% survival rate. Yet in peacetime, the decision to eject from a disabled aircraft is not always an easy one to make. In-depth analysis of aircraft accidents reveals that a number of psychological factors may be deeply involved in the decision. Situation awareness played an important role in a number of recent successful ejections. One, over the Nevada desert in late 1980, started out as a routine F-4G training exercise.
I'm Lieutenant Colonel Roger Ayers, stationed at George Air Force Base. Fly the F-4G Weasel on the 17th of December. We were up at Tonopah Electronic Warfare Range as I completed a strike shot on one of the emitters up there. Got a blink of master caution light. Started to climb out, and the entire caution panel had failed. As I checked the utility hydraulic pressure, it was down to 0. All other engine instruments read normally. Climbed up, leveled off about 13,000 feet and 350 knots. By this time had lost PC-1, PC-2, and utility. The aircraft started an uncommanded roll to the left. This time made a radio call that we were ejecting, and followed that by ordering the Evo to eject at that time. Watched him go through the mirror, and as soon as he cleared the aircraft, about 45 degrees of bank, I initiated ejection. Took until we were approximately about 130 degrees of bank, maybe 40 degrees nose low by the time my ejection seat fired. While the entire process took about 45 seconds from the first blink of a master caution light to ejection, the decision to eject probably was made back in pilot training. The aircraft was uncontrollable. I had no flight controls and no hope for recovery of the aircraft. If I had it to do over again, while I assumed a good position overall for ejection, I did not let go of the stick and did not pull the handle with both hands, and subsequently my right shoulder was broken during the ejection process.
While a T-38 flight crew was practicing landing procedures at a Midwestern base, the pilot and her instructor experienced a right engine failure.
I'm Lieutenant Julie Fee. As a student pilot, I was recently involved in an emergency in a T-38 aircraft at my home base. We came back from a routine sortie to do a heavyweight no-flap touch and go, and as we were climbing out, we got a fire in the right engine. We shut the engine down, but the fire burned through the control cables that led to the stabilator, and we had no pitch control. About that time, my instructor said it was time to get out of the aircraft. I said, okay, looked down and pulled my hand grips up and waited to hear him go behind me. Heard the boom, I squeezed my triggers, and that was the end of it. It was not nearly as scary as I'd always thought it would be. I'd been really bad in aerospace physiology training. I just hated parachute landing falls, and I was terrified of ever having to eject. I thought I'd never have to do it. But when it came time to do it, my instructor pulled me through. If I'd been solo, I think I would have thought about it a lot longer. But my instructor was so calm about it that it didn't leave me any second thoughts. I just squeezed the triggers and went. And it didn't hurt. Everything worked just like it was supposed to. I know if I was ever in a situation like that again, I wouldn't hesitate for a second to pull the triggers because it works like it's supposed to and it doesn't hurt.
Over the California desert, an A-10 was test firing ammunition with a new flash suppressor. Lieutenant Colonel Rusty Gideon was piloting the aircraft and can relate what happened.
About 3 years ago, I was involved in a flight test mission out of Edwards Air Force Base in an A-10 during which some problems developed, which caused me to have to bail out. The problem was a double-engine compressor stall, which led to a double-engine overtemperature, and then I shut both engines down, attempted to cool them down so that I could then restart them. However, ran out of altitude before having completed that full sequence, so I had to bail out. I've always thought that it's sometimes difficult, sometimes easy to make an ejection decision. The easy ones are when your wing gets shot off, or your engine blows up, or your flight controls lock up. That's pretty self-evident that it's time to leave the aircraft. There's other times when the pilot hopes he can salvage the situation, or he hopes things are going to get a little bit better. But by waiting that extra moment, it's certainly possible that you're going to put yourself out of the ejection envelope. In my case, there was some question in my mind as I descended through what appeared to me to be 2,000 feet, because I had actually seen one of the engines light off and begin its start cycle. However, I've never regretted the decision to bail out when I did, because I'm still not sure that it would have lit off and that it would have provided the amount of thrust I would have needed to recover the airplane. As far as the ride in the parachute, it was a little bit violent at first. It takes about 2 seconds from the time you pull the handle until you're in the chute. Then it was very quiet, and once my senses caught up with what was happening to me, it felt very comfortable. I'd been there before numerous times during the training, and the rest of the ride down was very comfortable.
While conducting high angle of attack tests on an F-111, another pilot was faced with an ejection decision.
I'm Colonel Pete Winters. We were conducting high angle of attack testing on the F-111. On this particular day, we were conducting accelerated stalls at 35,000 feet to check the departure characteristics of the airplane. We had already conducted one test in which the airplane did depart as predicted in a rolling departure and then recovered rather rapidly. We decided to go to our second point. The second point was an accelerated stall, 2Gs. The airplane departed as predicted, but then went immediately into a spin. I applied the recovery controls, and the airplane started to recover. We thought we were going to make it, but we were coming down very rapidly and passed through our spin chute altitude of 22,000 feet. I deployed the spin chute as briefed, and the spin chute came off in the maneuver. Now things weren't going as predicted. Both engines were stagnated. As we passed through our ejection altitude, and my chase pilot yelled for me to eject, which I did after very little thought. I don't believe that up to that point I'd even thought about ejecting. Because the airplane was highly instrumented, we went back after the accident to determine how much time we had. We calculated 3 seconds. If we'd waited another 3 seconds, the chute would not have opened prior to hitting the ground. I don't know that I would have made that ejection decision in those 3 seconds if my chase pilot had not assisted me and yelled for me to eject. I was highly trained and prepared for my mission. I was prepared for the departure. I was not prepared for the violent recovery maneuver and the spin chute coming off. I don't know that if I departed in the operational world, if I could have made that decision to eject. It's important to know when it is that you want to eject and then abide by that decision while you're in the air.
Even the crews of our newest aircraft models, the F-15 and F-16, have experienced unexpected ejection situations. The idea of ejecting never occurred to one F-16 pilot until he saw how close he was to the ground.
I'm Major Paul Rossetti. We're flying at low altitude on an F-16 operational test mission when I looked over my shoulder and saw an aggressor aircraft attacking my element. We made a defensive turn. After that, I made a wing lock. Shortly following the wing lock, my airplane pitched up violently and went into a falling leaf maneuver. I was surprised. I immediately focused all my attention on trying to fly the airplane back under control. After 3 or 4 oscillations, the nose pitched down, then it pitched back up again. At that point, I checked my altimeter and was reading close to target elevation. I then looked out the window, got a close-up on a cactus, and decided it was time to eject. The ejection occurred about 700 feet AGL, about 5 seconds after going out of control. The aircraft was in a very high sink rate at that time. It impacted the ground about 4 seconds after I ejected, and the 4,500 pounds of fuel on board made a fairly sizable fireball. I was forced to make a 4-line jettison and steer my chute to miss the fireball. If I had waited another 2 or 3 seconds, if I had not had any prior parachute knowledge, or if I had a less capable seat, I would not have cleared the fireball. 4 thoughts on my ejection. Firstly, when the aircraft pitched out of control, I did not even consider the option of ejecting, even though I knew I was at very low altitude. Secondly, I did not realize that the aircraft was not going to make it until the nose pitched down, back up again, and I looked out at the ground. Once I had made up my mind the aircraft was not going to make it and I had written off the aircraft, only then did I turn to the question of survival. And finally, things happen a lot quicker than you think you're going to. You don't have as much time as you think.
During a strike exercise involving multiple aircraft, an F-15A was involved in a mid-air collision.
I'm Captain Bob Devos. I'm an F-15 pilot stationed at Holloman Air Force Base in New Mexico. On October the 3rd, 1979, I was commander of a composite force training mission past a close escort F-4 fighter bombers into and out of the Fallon Naval Air Station Range complex in Nevada. As I unloaded and rolled away from my last kill, I instinctively rolled to my right, and what I saw ruined my whole day. Another F-15 on an imminent collision course. The mid-air collision severed the nose of my F-15, disintegrated the canopy and windscreen, and instantly blinded me. I immediately reached for the ejection handle and ejected myself in the Aces 2C at approximately 350 knots indicated airspeed and 20,000 feet MSL. The ejection sequence was both violent and instantaneous, very comparable to being fired out of the end of a shotgun. The most important thing about the ejection sequence was that I was alive. And the reason that I was alive was because I made the decision to eject, and then I executed that decision without any hesitation. I might add that I did not make the decision to eject on October the 3rd, 1979. This was a well-thought-out process over many years of flying. That is, my philosophy had always been, if I got myself into a situation where I could not determine the attitude or the capability of my aircraft, then I would eject, regardless of who was to blame. My message is simple and straightforward. If there is any doubt about the status of your aircraft, leave it. We can always rebuild the aircraft, but we cannot rebuild the pilots.
Speed in today's aircraft has doubled and quadrupled from that possible in older models only a few years ago. These higher speeds mean a reduction in the time a pilot has to perceive, to interpret, and to appropriately react. We no longer have the luxury of time to deliberate for a decision. You, today's aircrews, must be able to meet the challenges presented by the aircraft that you fly. The time to think about what you will do if an out-of-control situation occurs is on the ground. Up there, the solution must be automatic. If ejection is warranted, then it too must be without hesitation. We all knew guys who didn't.
That's cutting it mighty fine. But it does show that with present equipment, you do have the capability to escape successfully from some pretty hairy situation, if you play it right. The margin can be awfully tight. In this case, the pilot made it. Here again, he made it. Sometimes a pilot just gets in too deep, and there's no way out. Many fatal ejections didn't have to turn out that way. Many of the ones who didn't make it would still be with us if they'd really understood all the factors under their control and used them. Better knowledge of your ejection procedures, making an earlier decision to go, and knowing your ejection envelope. How about you? If you're like most, like this jock here, you've thought about punching out. You're very professional about the condition and functioning of your aircraft. But how much thought have you given to the system on which your life will depend if your bird lets you down? How about your part in the system? How about time? At high altitudes, you have time. But at low altitudes, time is of the essence. How fast can you be ready to eject? If you've got to think about each step in the procedure, you may think yourself into an early grave. So, practice. Get yourself in an ejection trainer and go through the procedure. It's been calculated that you can't get yourself positioned and pull the D-ring or face curtain to the canopy jettison stop in less than a second. Have someone time you. The practice may save your life at that moment of truth. It takes another half second for the canopy to release the interlock and for you to pull the D-ring or the face curtain all the way to effect ejection. Practice both methods of actuation. Get an idea of how far it pulls to the canopy jettison stop and how far after the canopy clears to the ejection point. Practice keeping your back straight and your head back in the headrest. You may get better leverage by leaning forward, but that puts your back out of line just when it should be straight and increases your possibility of injury. There are a lot of different seats in U.S. aircraft. Know the equipment in the aircraft you're currently flying. It's not very likely that you'd spend precious seconds fumbling for that face curtain handle in a 105. The one that isn't there, that is. But you'd feel pretty foolish if you survive. Know your equipment. Know it well. You're likely to be in a big hurry when that time comes. Study your flight manual. It's got the full procedure, step by step. Then get in a trainer's seat and practice. Once you've ejected, you can still keep your chances through cool actions. Unless your bird has a Martin Baker seat, you should try to beat the system, particularly in a low-altitude situation. You won't beat it, but you're ahead of the game if the system should fail. If it should fail, you've had your belt opened manually just about the time you started wondering when your automatic system would function. Remember, though, if your belt is manually opened, you've got to pull your own parachute ripcord. Do you really understand the zero lanyard? In Air Force aircraft, its function is to override the timer, giving you a chute up to 1 second sooner at low altitude. In Navy aircraft, the zero lanyard arms the parachute actuator as the seat leaves the cockpit. It's amazing how many pilots disconnected when they're doing low-altitude, high-speed work. They're afraid if they've got to go out fast and low, the lanyard is going to get them in trouble because of the danger of chute opening shock. It just doesn't work out that way. True enough, if you've got to go out above 450 knots indicated, you're faced with the effects of wind blast and flailing, but the chute will not be destroyed by the opening shock. The human body is just not very streamlined, and it slows down fast. The human form ejected into a 600-mile-an-hour airstream slows to 250 by seat-man separation. With a zero lanyard connected, your chute would open in 3.5 seconds at 160 miles per hour. That's why Air Force and Navy experience shows that out of nearly 6,000 ejections, not one man was lost due to chute destruction at high speed. One of the biggest causes of fatal ejection is delayed decision. If you don't eject in time, there's no equipment that can save you. This is not the best place to make up your mind. The earlier you make your decision, the better your chances. The best decisions are made in the pilot's lounge. That way, when the moment arrives, you don't waste time thinking. You react. In some situations, the decision is fairly clear-cut. If your bird is out of control at 10,000 feet above ground level or goes out below 10,000, get out. And that's a minimum. Check your flight manual. For some birds, it's higher. Even in situations like this, some pilots will try too long to recover, particularly if they feel the emergency happened because they goofed. There are a lot of factors that lead to delayed decisions. The desire to save the bird is a big one. The desire to pull off a difficult feat with skill looms large. Fear can keep you in that airplane too long. That familiar, solid cockpit can seem safer than going out into all that empty space. And then there's always the fear of being injured during ejection. If you do everything right, the danger is minimized, but the apprehension is there. These aren't good reasons for delaying ejection, but they are good reasons for thinking hard about when you'll eject before the emergency happens. Then you're in the position of making the clean, positive decision that adds another successful ejection to the statistics. But the really tricky situations happen lower down. Here's where you can get sucked in. You have control, and it looks like you have the field made. Here's where things can look right for a flameout landing at 1,000 feet. Then suddenly look very bad at 500 feet. At 500 feet, time is very short. Here's where you can yield to the fatal temptation to bring up the nose in an attempt to stretch that glide. Then you start sinking fast, and you know you can't make it. Here's where the real paradox enters the picture. Here's where too many pilots ask the impossible of ejection equipment. That ejection alternative seemed like a very unpleasant choice back upstairs. But now that things are going clearly against you, you may put too much confidence in its capability. How does that happen? It seems that each time an improved ejection system is introduced, the success rate decreases for a while. It looks as though you expect too much from the added capability. So you drive a 106 or an A7. Haven't you got a 00 seat? Haven't you got it made right down to the deck? Granted, when you see a demonstration like this, it sure looks that way. But that 00 terminology was a poor choice of words. It's true if you're parked on the runway. But if you're not parked, those zero-level figures can lead you right to oblivion. They leave out one very important factor: flight vector. Airspeed, attitude, and altitude are the terms usually used to define the limits of safe ejection conditions. So, let's look at two high-performance birds with two of the factors, airspeed and altitude, the same, but their attitudes are different. One's inverted, with its nose 15 degrees above the horizon. The other is right side up in level pitch attitude. They both have 235 knots airspeed and 100 feet altitude. If they both eject at this point, who has the best chance? According to the usual criteria, airspeed, attitude, and altitude, it looks pretty simple. But in fact, we don't have enough data to decide. For example, if the inverted bird has full power and Mr. Right Side Up is flamed out, what looks so obvious becomes a brand new ballgame. Simple flight dynamics put the inverted bird in a 15-degree climb, and the one that is right side up is descending on a 15-degree glide path. The aircraft's flight vector will be the major factor determining each man's ejection trajectory. Mr. Right Side Up will impact the ground 2 seconds before full shoot, while Mr. Upside Down will make it with a few feet to spare. Hard to believe? Let's see how it works. Think in terms of time. In the case of an F-4 at 200 knots, time from leaving the cockpit to full shoot is approximately 3.5 seconds. Here's how it works. At 1 second, the drogue gun fires. The drogue chute stabilizes the seat, and the main chute is deployed. The force of deployment causes seat separation. By 3.5 seconds, you have full chute. Remember, that's for an ejection at 200 knots. But at 100 knots, it takes almost a full second longer for the airstream to deploy the chute. Seats in other aircraft vary in their sequencing. For example, with a 200-knot airspeed and the zero lanyard not connected, here is the action. It pays to know your time required to get a full chute, which ranges around 4.5 seconds. However, for simplicity in what follows, we'll use the 3.5 second figure as the time required. Now, let's look at the other side of the coin. Time available. Time available depends on a lot of variables, but they all boil down to directions and velocities, that is, vectors. Let's look at the vectors of the ejection seat. This is one of the first variables, since there are a number of seats in use with varying boosts provided by both ballistic charges and by rockets. The vector provided by the seat will differ according to the amount of boost and its duration. To keep things simple, we'll stick to one value, 100 feet per second effective. But here again is one more reason to be familiar with your own seat's characteristics. The next variable is aircraft attitude. When you're straight and level, the seat boosts you almost directly away from the ground. Any change from level attitude, either pitch or roll, reduces your upward seat vector and therefore subtracts from time available. At 45 degrees, you lose 30% of your upward vector. At 60 degrees, half of your upward vector is gone. At 90 degrees, there's no upward component left. If you're inverted, your seat boost is subtracting from time available. The vector resulting from flight path is the last and most important variable. Let's look at some examples. Using ejection altitude as your reference line and a line in the 10-degree flight path with a length proportional to its airspeed of 180 knots, which is 300 feet per second, the vertical component of its travel is 52 feet per second. The 100 feet per second vector of an ejection seat at right angles to the flight path gives us an effective upward seat component of 98 feet per second. These two upward vectors add together to give a total upward vector of 150 feet per second at time of ejection. That would result in a trajectory which would carry you about 300 feet above ejection altitude before gravity and the deployed parachute slow your climb to zero and you begin your descent. Now, let's consider the case of an inverted aircraft with the same speed, 180 knots or 300 feet per second, in a 30-degree climb. The vertical component of flight path is 150 feet per second. Since the aircraft is inverted, the seat thrust vector of 100 feet per second has a downward component of 87 feet per second. Subtracting this downward vector from the upward vector of 150 feet per second, you still have a net upward vector of 63 feet per second. You will continue to gain altitude for 2 seconds before beginning your descent, and you'd have full chute about 20 feet above ejection altitude. The situation changes drastically with a descending flight vector. In a 30-degree dive, 240 knots airspeed, or 400 feet per second, half the airspeed is converted into descent, 200 feet per second. The ejection vector of 100 feet per second provides 87 feet per second upward to counteract this, but the net vector is still 113 feet per second downward. This man is shooting himself at the ground. The chute still takes 3.5 seconds to open, but this time that will be about 600 feet below ejection altitude. Unless he has more than 600 feet airspace, he buys the farm. With this same example, if the pilot had traded airspeed for up vector using the zoom maneuver, we'd have a very different picture. Let's say he established a 10-degree climb and went out at 120 knots. That's 200 feet per second, with an up vector of 36 feet per second. The seat boost of 100 feet per second gives an effective 98 feet per second upward seat component for a total ejection vector of 134 feet per second. This gives him an open chute at the top of his climb, about 250 feet above ejection altitude. That's a pretty good trade. Airspeed for up vector. But what about altitude? Remember, raising the nose may or may not increase your ejection altitude, but it gives you better survival potential due to a more desirable seat vector. An instrumented zoom capability study on the F-8 under simulated flame-out conditions shows that a zoom maneuver started from level flight at airspeeds between 185 and 220 knots results in a net altitude gain. By contrast, zooming up from a glide results in net altitude gains at 200 and 220 knots. But because of the glide angle at 240 knots, the zoom results in a net loss of 100 feet. Let's look at the case of the net loss. With a flame-out at 240 knots at 500 feet, a maximum glide angle is established. The bird would be on the deck during roundout and would zoom back up to 400 feet as ejection speed of 130 knots was reached. The ejection vectors look like this. 130 knots or 220 feet per second in a 10-degree climb gives a vertical component of 38 feet per second. The seat vector of 100 feet per second gives an effective vertical component of 98 feet per second. Total ejection vector is 136 feet per second. It will take 4 seconds to halt your climb, at which time you will be about 250 feet above ejection level. In free fall, it would take 6.5 seconds to reach the ground from here. The zoom put you in trajectory for a total of 10.5 seconds, 2.5 times as long as if you'd gone out at 400 feet on the way down. However, using the 3.5 second chute opening time, you had full chute before you started your fall, which gives you a nice margin. To get the same margin in the gliding situation, you would have had to eject at about 1,400 feet instead of at 400 feet. Actual tests with line pilots in F-100 simulating the zoom maneuver showed they were able to convert a 35-knot excess above touchdown speed into an average peak rate of climb of 690 feet per minute. The average altitude gain was 160 feet. From this, you see that you can zoom and eject from a flame-out on final down as far as flare. It should be very clear by now that in low-altitude escapes, flight path is more important than altitude or attitude, that high sink rates can cancel the boost of our most capable escape equipment, and that if you've got control of your bird, your best safety reserve is air speed. Air speed, which you can trade for an up vector when it's time to go. The zoom maneuver, zoom and boom, can give you that margin when you most need it. A good example was the opening sequence. The RO went out at 75 feet. His ejection vector gained him an additional 200 feet. The pilot went out at 250 feet, at the top of the aircraft's climb. Without up vector from the aircraft's attitude, the pilot gained only 25 feet and had full chute at 69 feet. The equipment's got the capability to get you out safely if you make use of those factors under your control. Know your equipment and procedures, and know them well. Make your decision early so your actions will be positive and correct. Understand ejection vectors so that you won't expect more of the system than it can give.